Can you hear me okay? Picking up on that? All right. I had to sneak a warm-up in. What I wanted to do initially is, this is a little stunt that I like to do with my students and when we get into acoustics and waves and sound, is Bill mentioned earlier it takes a couple of liters of air to be pumping air through those open-ended pipes like that to get the tones to come out, the harmonics, and you have to really blow pretty hard. And I like to think I'm blowing pretty hard when I play a trumpet. Trumpet players have egos. Nice and loud here. This is an ego chamber, by the way. Now, the thing I'm going to do now is I'm going to pit my physical strength against a bubble. See if we can do something a little interesting here. But I just could not muscle a bubble about 1 molecule thick. What's going on here, obviously, is the drift velocity, the airstream in the horn is very slow compared to the speed of sound in the horn. You can actually calculate it by measuring the change in volume. There's a journal article in the International Trumpet Guild that explains how to do that. Turns out the airspeed, there was a physicist who did this in their group too. The airspeed in the lead pipe's about 4 miles an hour. You can't even blow out a candle like that. So next time you got some hotshot trumpet player in the band at school, he thinks he's tough, tell him he couldn't even blow out a candle when he's holding a high C. See how he likes it. Now, you can do this little stunt with trombone, French horn. You can do it with trumpet players, but in high school it's kind of hard to find. I teach in high school, obviously, duh. And it might be a little difficult to find trumpet players who can do this with their instruments because you have to play rather high. This is a C trumpet. This is a natural C trumpet. I'm going to venture into the turf of Punnsville here. This is actually a genuine replica of a broke trumpet. I won't even bother. I'll let you fill in the blanks. Okay, but this thing is a pipe. When I put it up to my lips, is it a closed-end or open-end pipe? All right, closed-end pipe. Now, we already know from Bill Shank's demonstration that when you play an open-end pipe, you get all the multiples of the fundamental, 1, 2, 3, 4, 5, 6, 7, 8. Well, whenever you have 1, 2, 4, 8 powers of 2, you get octaves, okay? Now, with a closed-end pipe, even or odds. You get odd multiples. So I should not get any octaves on this thing. Let me see what I can come up with. That's an octave. Another octave. Put some physics in this. So the question is, whoa, closed-in pipe, what's up? I've got even multiples, I'm getting all the octaves, I'm getting everything. How come? Okay, if you find some books by Tom Rossing, or there was an interesting article by Arthur Bonatti in 1974, Scientific American, they explain that rather nicely. That's a cylindrical pipe you get those odd multiples for when you have a closed-in pipe. This is not cylindrical. You get a nice tapered bell and a mouthpiece. It changes the ball game significantly. If you want to play around with your more advanced students, there's a lot of physics involved in trying to explain how a trumpet works. Tons of it, but I am done now. Thank you very much.